apologize. That is a remnant of cutting and pasting from many slides. I'm no longer at UNC Charlotte. I'm at North Carolina State University, which is on the bottom of the slide here. And they are different schools. They're about 3 hours apart in North Carolina. So I wanted to start out with my guiding principles for research. And how many of you have ever applied for IRB? Okay, good, everybody. So how many people like doing that? It's not fun, right? But if you go back and you look at the principles and the reasons why we actually do apply for IRB, they're actually beautiful. So I wanted to remind you what they are. They're respect for persons, beneficence, and justice. So these are actually the ways that I pick the kind of research that I do. I use these 3 principles to decide, is what I'm doing actually worth spending all this time on? And the reason why I say that is because in educational data mining, and I can't make any claims about learning analytics people because this is my first learning analytics event, but I know that in educational data mining we often make the mistake of, or I think, in my opinion, I think we make the mistake of trying to get that better model that is statistically significantly better than the previous model, but not necessarily saying what difference is that going to make in the educational experience in the students that are using this system. So what if I can model your knowledge, 5% better than I could last time? Is it going to make a difference in how many exercises you have to do on your homework? Probably not. Maybe one less, one more. Is that really a big enough difference for students? Is anybody going to actually use that? Well, if they can't read your paper, no. So I just wanted to say these are the kinds of things that I try to think about when I'm choosing what research to do. And so I actually have also listed the kinds of things that I think we can do based on these principles when we think about adapting systems. So I know that learning analytics has many different levels of analysis that people do at system levels, institutional levels, countries. You can be at many different levels. So most of my work is at the individual student level. So that's what I'm going to focus on today. So if I'm thinking about those levels, here's how we would apply those principles. So when we think about respect for persons, we're going to make choices that are going to make a difference for individual people, and that's why I really loved Phil's talk from yesterday. I hope I got your name right. Is it Phil? Okay, good. I really love that because it was like, so what? What difference does it make for me? And that's really what I'm thinking about when I'm doing my research. So when we think about that, we want personalized models. You don't want a teacher that doesn't care who you are. And you don't want an educational software system that doesn't care who you are and what you've been doing and what you could do. And I also like to put in that I recognize that people have a lot to offer to learning environments and to one another. And I think that this is something that has distinguished my work from many other people's. And as I'll show you, most of my work has been in taking data from students interacting in learning environments and using it to give feedback to other students or give hints to other students. And when I first started doing it, people said, well, how can you possibly get good hints from other student work? As if students had no knowledge and had no ability to do anything that might be useful for anyone else. I feel that as a teacher, I'm constantly learning so that when I'm trying to figure out the best thing to give to my students, I'm having to learn new things. I'm a learner as well. I'm a student as well. So I wouldn't want to say that no students have anything to offer, right? And then also, my other answer when people say is, how could you possibly get good models from other students? I say, don't you ever give any A's? And most people say, yeah. I'm like, well, I could take the data from those students that had A's and use it to give feedback to other students. And then they're like, oh yeah. Like, we just forget that there's expertise being built in the classroom at the time that we're doing things, or being built in our learning environments. And those processes are a lot closer to what students are experiencing than what we experience. So I like to think about the idea of an expert blind spot. So how many people have heard of an expert blind spot? Okay, so most people have heard of it. But the idea of the expert blind spot is that once you know how to do something, it's really, really hard to explain to someone else how to do it. Because we've actually sort of put that knowledge together in our brain, and then unless you've consciously thought about how you learned it in the first place, you may not actually know the best path to take new learners down. But somebody who just learned it yesterday, they know how they got over that hump. And so when I'm taking student data, I'm actually really leveraging the current experience. And so I liked Carolyn Rosé's metaphor at the end of her talk, is that if you take the M&Ms and you take all the colors off, you're losing all that data. And that's what I like to say, is that data in the middle of someone learning is great data to give someone else some adaptive experience, someone else who's coming along. So that's what I like to look at. Then when we think about beneficence, that's sort of like, what difference does it make? So in that case, that sort of gives us all the directive to look for practical effect sizes. And so I think that that has been a trend lately, people thinking about, okay, so not only do we have statistical significance, but do we have something that actually makes a difference in terms of, like, is a letter grade going to change, or is someone's amount of time they have to spend on homework going to change? And then I think also, in order for us to make a difference, I think instead of constantly arguing about what models we ought to use for something, sometimes we ought to just pick some so that we can all talk across systems and use each other's advances. And then, like I said, also we want to maximize the potential of all of our research to result in positive changes in all kinds of educational systems. And the third principle for IRB is justice. So maybe next time you're doing your IRB applications, you won't be so upset about having to do them. Or maybe you'll volunteer to be on an IRB board and teach people to be more beneficent to the IRB application writers. But anyway, the third principle is justice. And so I use this a lot when I'm designing my research studies. So especially in the education area, like if I think I've made a new system or a new way of teaching something or a new method that's going to be better for students, it's actually not fair for me to do these controlled experiments, right, where one classroom gets the intervention and another one doesn't. And also they talk to each other. It's all kinds of annoying. So most of the time when we do educational experiences, I've done switching replications or crossover studies where you have half of your students try the intervention, half of them are the control group, and then they swap. The ones who try the intervention first get to do whatever you had the control group do, and the other group gets the intervention. And that turns out to be a very nice method because you basically have a control study for the first half of your study, and then the second half tells you if there's any ordering effects. Because most of the systems I'm working on are actually for homework for students to solve problems and practice solving them. And so there's multiple opportunities to give more homework. Most teachers don't complain when I say, hey, can you have another homework assignment in their class? And I go, well, I don't have to make it and I don't have to grade it. Sure. And it's another opportunity for the students to learn in a different way. So I have seen that has been good. But also, we want to think about considering equity in developing and deploying our systems. So, I'm working all of us are working in digital spaces, most of us, right? Is there anybody not working in digital spaces? I mean, that's what we do, right? Okay, so good. A few of you are still helping people who are on the other side of the digital divide. So I do think about that, and we want to think about, so when we're putting all this effort into figuring out what digital systems should do, we should also remember that not everybody has access to them. And so at the same time, I try to do some work that actually increases access for people to digital education. I also try to remember that there are a lot of ways to demonstrate and measure proficiency and mastery. And so I think that a couple of the talks yesterday mentioned, the desire that we all would like to have to do self-assessment, to be able to figure out what someone knows, just by the behavior that they have in the systems that we give them or the experiences that we give them. And I think the more that we can do for that, the better, instead of having these high-stress environments. And there's been some great work in those areas, especially Neil Hefman and Zach Carnes and several people in the EDM community have done some things that have actually showed that they can predict test scores, and if you can do that, why do you need to have the test? So just wanted to start with those. Excuse me. So last year I was asked to think about what might win the Best Paper Award at Educational Data Mining 2023, like 20 years from then. So actually I thought I'd start here by telling you what my vision was, since many of you may not be going to the EDM conferences and thinking about, but I think we all think about the same things. Like, we're a community of people that wants to improve education, and we want to use data and analytics to do that. So I think we have a lot of overlaps. So I think we need to have some different ways of recognizing and promoting excellence in teaching and learning. So like I just mentioned, non-intrusive models that can recognize mastery are wonderful ways that we can actually identify potential people that might help other people. So the thing I always come back to in the systems that I think about are how do we either connect people to each other or connect people's data to each other to help the process of learning. And so if we could recognize mastery, we could recognize people that might help other people. Even if we can't sort of make a fully automated system that's going to build hints, what if we could, hook people up? That would be awesome. And what if we could do it in a way that they weren't annoyed? that would be super awesome. And I do a project, an intervention, I guess, in my discrete math class that I have taught since 1996. And I invite students after the first few assignments to become peer tutors if they have done well in the class. And what they have to do is provide 10 hours of service to my class in return for not taking the final exam. And so out of 250 students last fall, 65 of them signed up for the peer tutor program. So they had to have an A on the first few assignments. And then if they did 10 hours of service, they could skip the final. And the students were elated about it, and I was elated about it, because I had 35 of those 65 students finish their 10 hours. And the 10 hours includes answering questions from other students on the forum, holding in-person office hours, making worked examples and posting them on the discussion forum, taking videos of my class and chopping them into pieces that make them more digestible for other students. So any of those things, as long as they did it and documented it, it counted. That's 350 free hours of work I got out of students that were excited to do it because they didn't have to study the last week of class. And also, most of them said that it was a way for them to make sure they learned the material better, because many of the students who were making A's in the first part of the class felt that, they sort of got it right away. You know what I'm saying? Like, there's always a lot of students that sit in your class and they're just like, everything you say makes sense, and they turn their homeworks, and everything's fine. But then when they have to help someone else, and someone asks them a question, they're like, I didn't even think about that. I didn't read that way. And so they have to think about things a different way, so they learn more. So also, I think in the future of sort of the best learning system I can think of in the future, we would have real-time support for an effective culture of learning. So identifying when and where potential collaborators might be working on similar tasks and putting them together according to a maximum likelihood of a beneficial peer learning relationship would be super awesome if we could do that. And maybe suggest joint learning activities that would be both fun and beneficial for people. And then also identifying proactively and also on demand hints on how interactions might be most helpful would be really awesome. And so all of these are, in my view, blurring the boundaries between teachers and learners. People have a lot to offer to one another, whether or not they are standing in front of the room or not. And so I think also we should encourage people to make content for one another. And so there's been some work in that in some systems, but not in such a way that's sort of scalable. So I'm interested in scalable ways to allow people to generate content. How many of you play any video games at all? Okay, so like a third of you play some video games. And how many of you play any games that have any user-generated content? Okay, much fewer. But games are starting to identify that. So there's a game called Little Big Planet, and people can make levels for one another, and then in the game you can play other people's levels. I think that that's a beautiful way to make systems actually more replayable, reusable, and having people make content for one another is a perfect way to do that. It's hard to do, so we've done it in some systems, and I'll show you some screenshots later of Beadland game, but when the key, if you want someone to continue learning while they're making content for other people, is to make sure that when they create the content, they're actually learning the content that they're doing activities that are related to the learning when they're making that. So there's definitely some things we would need to do to get to these kinds of places. And one of the things I think we need to do is to have a system where people can kind of keep track of their achievements. And if you're an Xbox player, you've heard of achievements on Xbox, but to take some of the idea from games, it's like keep track of, hey, who am I? What am I good at? Having a system where everybody could have their own information on what things they have learned and what they're able to do would be really cool. Sort of like your credit score, only your I know it, my list of stuff I know would be really neat. And it would be neat if you could sort of provide a key and say, yes, this system can have access to my I know it page. And use that to adapt the individual experience. And we have a lot of diverse learning environments, so we have to have some kind of interoperability between these kinds of systems that tell about what people know. And we have to get better at detecting like when someone has become a master. And one other thing I just wanted to mention here is that relationships are super important for learning. I mean, so when I think I'm a computer science professor. How many people in here are computer scientists? Okay, so maybe half. So in computer science, we're terrible, terrible educators. Don't tell anybody I said that. We really are. It's because we all learned by doing it ourselves, and then we get in front of the class and we're like, go do it yourself. That's how you learn it. And the students are like, what? But we're serious because all of us actually fell in love with something. You know, if you're a computer scientist and you love being a computer scientist, you fell in love with something, you figured something out by yourself, and you felt like you conquered this machine, and that's what you think everybody needs to do to learn something. Well, maybe that isn't what everybody needs to do to learn something, but there is something to relationships and emotion. There's a lot of important things, and I think that if we could figure out how to leverage those things in educational experiences in more diverse ways, that we would be stronger in general. And I always like to have in my talks pictures of all my students because I'm about to tell you about all the work that we've been doing, and I actually didn't do most of it, so most of my students did them. I have stars next to students who have graduate research fellowships or other NASA fellowships, and white stars if they got honorable mentions and wish they had that money. So here's some more of my students, and they're younger, so they haven't had a chance to apply for fellowships yet. And so as you might be able to tell, I do some work in games. I also do a lot of work in getting more people into computer science, and I'm going to tell you more about the AI for learning. And I did want to mention at NC State we have two cool centers. We have the Digital Games Research Center and the Center for Educational Informatics, and I'm in both of those. And it's kind of neat to be at a place where we actually care about using information to improve education. And we also build games and educational games, and we do research on how those can be more effective, so it's a neat place to be. And as Nicola mentioned, I have a career award that was awarded in 2009, and for educational data mining for student support interactive learning environments, and I'm going to tell you about the evolution of the work that led to and has been coming from that support. So as I was mentioning before, my vision is sort of building systems that can help individualize instruction for people and create a shift in teacher roles, focusing on human interactions and engaging and inspiring students. And so I've been working on what we're trying to make as domain independent as possible systems for understanding learning and using that data to help other students. So this is a picture I actually made for my PhD defense. Is that students are actually interacting with the computer. We have lots of data about that. And if we could use data mining to build intelligent feedback and control, we could affect learning. And I have this screenshot of the Educational Data Mining 2008 conference because I was chair of that. And so we are about to go to London and have our 2014 conference. And it has grown from about 70 people to over 200. And this will be our biggest year ever. So I'm very excited about that. Okay, so my work is based on a lot of theories underneath intelligent tutoring systems. So two of the parts of an intelligent tutoring system, sort of in the cognitive tutors approach, have been to have both what are called a model tracer and a knowledge tracer. And so knowledge tracers are being able to tell what the student knows. And a model tracer is when a student is solving an individual problem, you have a model of how people solve the problem, and you kind of trace what the student's doing on that model. So this is like the oldest conceptualization of tutoring possible, is that you think of, you know, if I'm going to measure a student's performance, I can have like an expert solution and then trace the students on top of it, like even with tracing paper, you could think of that kind of analogy there, is that I'm actually tracing what the student's doing on top of what I predict that they might do. And at first, it was sort of, we just had correct models, and then people started also building models of incorrect behavior. And so then you use that to sort of diagnose what the student's doing while they're solving problems. So my goal has been to make data-driven or data-derived model tracers. And so most of my work has been in discrete math and teaching logic proofs. The nice thing about logic proofs is that they are open-ended. People can do whatever they want in a proof. And how many people know what a logic proof is? Okay, almost everybody. If you don't, just like think back to that time you blanked out in your memory of doing geometry and you were given a few premises, like some things that are true, and said, okay, given these, prove this other thing, and you're just supposed to use whatever tools you learned in class so far. And most students hate that, because they're like, what am I supposed to do? They're like, well, you're supposed to figure something out. So that's nice, but it's also nice in that the activities they can do are constrained. Like there's a list of axioms you can use, and that's it. You can't do other stuff. I can't just be like, no, I want to draw a flower. Like, it's just not going to happen when you're doing it. So I can have a system that's open-ended, but also I can understand all the things that students are doing in it. So what we've done is we've actually looked at students' proofs that they make in these open-ended environments, and we make a big map of what they're doing. So we make a graph of what students are doing. So you can think of taking a screenshot of their learning environment, and that's like a state. And then, like at the start, and then when they do something and the screen changes, we take another snapshot, and we have an arrow in between those two states. So that's like the basic level of a graph, and I'll show you some pictures of that, of what we're thinking about when students are doing solving a problem. Then we take all of those from each individual student and put them together into a big graph, where if two students have the same screenshot, they get put in the same state, and we just increment the number of people who visited that state. And if they don't, we have separate states for them. We put that all into one big graph. And then we calculate transition probabilities based on frequency of students actually going in between states. And then in that big graph, we actually label some of the states as good solutions. And we also give some labels to things if we know that they're errors, which our system actually recognizes if you do some stuff that isn't good. We can actually label those as errors and put a -10 on those, and we label good states or solutions as with 100. And this is using a Markov decision process, which is an AI kind of data structure. And then we use an algorithm that assigns credit to states according to sort of if they ever get to a reward state. And if that doesn't make any sense to you, you can just think about the idea that we know where someone ought to go, and we can see what's connected to the places where they ought to go, and we can back propagate the sort of value of being in a state according to whether it ever gets to something that's good. So the cool thing is that we came up with a method to assign a value to everything that anybody ever did in our environment, even though we didn't have an automatic way to grade what they were doing. And this is a picture you're not supposed to be able to see well of a graph of what everybody's doing when they're solving a problem, which takes about 10 steps to do in a logic proof. And the reason why I'm showing you this picture is to show you that even though there's a bunch of gobbledygook in here, which I would call spaghetti, there's some in the middle where there's a whole bunch of overlap. Can everybody see that? Okay, and so each line is an individual student. So you can see if there's a whole bunch of lines going in between two states, then a whole heck of a lot of students did the same thing. And what a coincidence, they're all in the same class. And they're all solving the same problem. And they've all been taught the same way. So, you know, if you've ever graded any papers, you get this feeling of deja vu, like half the time, right? So students do stuff that's similar to each other. And that's what we leverage in order to use this to give hints to new students. Okay, so that gives us likely paths that students take. So if we see a bunch of overlap, that's something that's more likely to happen than not. And we also have a value for each state, like I mentioned to you. And the value actually can help us choose. If I can see where a student is in this graph, you know, I'm tracing them, and I say, okay, you're right here. Well, only one student ever did that, so that's not super useful, so it's better if I'm over here. And if I'm in this state, well, there's like 4 or 5 different things that people did from there, but since I have a value on every one, I know which one was actually the best one. So I can choose that one and say, I'm going to use that to generate a hint for a new student. And so this is useful in any kind of domain where we have open-ended problem solving that are sort of very structured, so procedural problem solving domains. So it's kind of getting at the procedural question from yesterday. What do we do when people are learning processes? Well, we keep track of all their steps because we need to do it anyway to tell whether they're actually solving the problem correctly, because just getting that final picture of what they did is like too hard to do anything with. Like I said, the state features are generally describe what the student sees on the screen as long as everything they've done so far is there. And in the logic domain, the state is described by the description of the problem, like what was given and what you were trying to derive, and everything the student has derived so far, and what rules they use to derive it. So I have been teaching discrete math since 1996, and I've had a lot of students. And I taught it both at NC State when I was a graduate student, and then at UNC Charlotte when I taught there. And then I met a philosophy instructor that was also teaching logic, and he was teaching proofs, and he had also built, we both had systems for teaching proofs, software systems, and I decided that students would like his better because mine was on the old Novanet system. Anybody heard of Novanet or Plato? My advisor was Dr. Donald Bitzer, who invented the plasma display, but was also one of the first educational system researchers. And so students don't like to use systems where they have to use Control-B instead of a giant button that has a back arrow on it. Like, it's very, very little of a difference, but they think they're on something crappy if it's not in a browser. So we started using the Deep Thought logic tutor, which is graphical, and we're rebuilding it right now because the browsers don't support Java anymore. But this is what it looks like, and we have, I bet you that I have an animation that shows what the parts are. Oh, good. So we have the workspace, which is the blue area. That's where students are driving new things. We have what they're given at the top. Those are called premises. We have conclusions, which is the thing at the bottom that they're supposed to prove. There are rules that they can use. So like I was saying, there's well-defined steps that you can take. And then there's some problem details at the bottom. And what the students are trying to do is use the rules to make new states in the middle to make sure that there's no question mark above any statement in the picture. So when you first start the problem, there's a question mark over the conclusion you're trying to solve. So I have a partially finished problem in here, and they've actually said, okay, well if I had some things, then I would know L is true, but I still don't know yet whether B is true, but I need to justify that. So here's a state example. So here's a screenshot of what it might look like when someone has done exactly one step in the proof. So the state list in text is to your right and the screenshot's on your left. So it's basically a direct mapping of what I'd have in the screenshot to what I would write in a text file for the state. And then here's another one. So 2 steps have been done. So after the initial givens, which are up to not D and E, we would add not D and A and B because those are all, B is the conclusion, we put that last, and the other things are the things the students have arrived. And all the actions that take students from one state to another are the rules that they can click in the environment. And as I mentioned before, we set our goal state to something with a high value, set error state with a negative value, and all other states start with a 0 value. And we also add a transaction cost each step. So if any of you, a lot of you are computer scientists, so you know that we like efficient things that are shorter. So we say, okay, a shorter proof is slightly better than a not shorter proof. So here's an example of making a graph with someone's solution. So they made an error. We do have error detection in the tutor, and it tells them if they've made an error. So if they have an error, we'll send them off into a side state and sort of mark that as an error, but then send them back because we delete what they just did in the error in the tutor. I've taken some data from tutors that don't do that, and so then we leave the error information in the state. So that's a picture of a student's signal graph. And so before we actually built a system to do this, since people are sort of nervous about like, oh, what if you give hints that would mess somebody up, we did a study where we actually looked at our past standard log data, and we said, hey, can we actually generate enough hints to make this useful? So we wanted to see, could we use data to give students 50% of the time? Just any time they're in the tutor, can we get at least a 50% chance that they can have a hint? So we actually looked at every single state, and then we said, okay, can we give a hint there? Sorry, the sequence of slides is different than what I expected. Okay, so in the hint sequence, what we do is, like I said, we look at the next state. So if I'm in a current state, I look at the best next state, and then I generate a hint based on what that best next state is. And that's domain dependent. But the model itself, you can see like the trees we make, they're it doesn't matter what domain we're in. The actions could be any actions you have in any environment. But we get the hint sequence. In this particular case, we say, okay, here's what you should try to derive. Here's the different boxes you should click on to do it. And then we also have a fourth level, a bottom out, that tells them exactly what to do. And so it looks like this. We have a pop-up window that says try to derive if n and t working forward. And then if they hit hint again before they do something, we say, well, you might need to highlight if not t, then not n to derive that. And then click on the transitive rule. And then do all of that stuff in order to do the very next step that we're hinting you to do. So has anybody thought yet, it's nice to hint them to the next step, but isn't that like cheating? I see some smiling faces, so some people might think that. So we actually have looked at how often students use our hints, and they use them on average, like they use an average of 4 hints. And what that means is either they get 1 free answer, or they get 4 nudges, somewhere in between there, because they can have either a depth 4 on the single hint, or they can do like 4, initial hints. So they're not getting that much. And then other people say, well, can't you give some hints that are sort of like more like what a teacher would say? And the teacher would say, oh, well, think about modus ponens, or what are the actions that they could possibly do? And then I look at my own self, and when I give hints to students, I don't always stay at that high abstract level. Although we actually do have some work, and I'll show you that, in actually getting more abstract level for the hints. So we took 4 semesters of past data for a single problem. We had 523 valid student attempts, and 73% of them were finished and complete. We compared across semesters to see how often we could give a hint. And so we did a cross-validation across all of these. And so what we did is we would say 1 semester of data, and then use it to predict all other 3 semesters. Then we use 2 semesters of data, and then predict the other 2 pairs, and then 4 semesters of all 4. We did that. And we had a few different kinds of hints. So if you're thinking about, okay, if I'm going to give this kind of hint, I'm basically like looking at someone else's homework who has worked a problem exactly like me all the way up to now. And that's pretty cool, because if you think about Vygotsky's zone of proximal development, a person who has worked a problem exactly like me in every single step is highly likely to have the same mental state and learn the same stuff as me, and I'm probably able to do the same stuff as that student. So when they give me that hint of what to do next, it's based on what somebody did, a person who's done a job exactly like I've been doing it. That's a nice kind of hint. So that's what our first kind of hint is that ordered hint, when all the states are ordered in exactly the order that you have done them. And when I pick a student to give you a hint, that student has done exactly what you did. Now, unordered is, maybe I can't find someone who did something in the same order as you, but I can find someone who did all the same stuff so the screenshot looks the same. Then, okay, I can give you a hint from them. They probably kind of have a similar mental model to you too. The last 2 are from the idea that a lot of times when someone needs a hint, they've already tried something that didn't work. So sometimes when we try to generate our hints, when someone would need a hint and they'd ask for one, they would have just done something that was kind of wonky, and other people hadn't tried that. And so when they asked for a hint, we couldn't give them one because the last thing they did wasn't matching with something else. So we tried this -1 attempt. Like if they're asking for a hint, maybe the last thing they did isn't their favorite. And so we delete that, and then we do the ordered matching and the unordered matching. And so then we got higher and higher levels of ability to give hints to people. And so we were really encouraged by this because we were hoping for 50%. And then if we use 3 semesters of data and sort of taking off the last step and matching somebody with someone who did everything except for one thing that they did, then we got 94% ability to give hints. And so that was awesome. But then we also wanted to say, well, how long is it going to take us to get to be able to give these hints? So like, do we have to go a whole semester, or could we incrementally add students to our model, and then when could we start giving hints in a reasonable amount? So what we did is we said, okay, let's take all of the student attempts, randomly choose one of them, and add it to our model. And then take the next student randomly and say, can I give them a hint based on what's in my model so far? And then repeat that randomly, and then do that 10,000 times. And we actually found out that in order to give hints, a 50% chance of being able to give a hint, I only needed 8 students if I had unordered hints. I only needed 11 if I used ordered hints. And we thought this was amazing. So we said, this is a good idea, we should build this hint system. So then we did a pilot study. We added hints to our logic proof tutor in 4 problems, but we only actually had 16 to 26 actually attempts that we put into the system for those problems. Because this is when I first started working with a philosophy professor at UNC Charlotte, and I only had data from like 1 semester of this stuff. And we tried it with 40 students in his class, and so we really only actually had hints for 45% of their steps. But 90% of the hit requests were successful. So what it turned out is not only can we give hints a lot of the time, but even with just a tiny bit of data and the probability that we could give a hint on any given thing is only 45%, we could give hints 90% of the time when somebody asks for one. What does that mean? Well, what it means is that students have a lot of overlap in where they need some help. So at first I thought students would get stuck like all over the place in proofs, but they don't. There's just a couple of key hard spots, and they're the same for a lot of those students. And so that's where we're getting a lot of leverage there. Also, we found that more students were able to do more problems when they had hints, and that's not a super big surprise. But we actually have found that after we implemented the system again and we did a bigger study, we found that students were 3.5 times more likely to finish the whole tutor if they had hints on the first few problems than if they didn't. And that's incredible. But then when we tried to look at the time in between our control groups and our experimental groups, we didn't find a time difference. And the reason for that was that a lot of students in the control group dropped out. And the regular professor response to that is, oh, since they didn't have hints, they gave up. Right? Like that's our cynical response to, if they're not getting it, they're just giving up. Then when we really looked closer, and I'll show you some more about this in a little bit, when we looked closer at the data, we found out that the control group students were spending more time in the tutor than the students with hints. They were giving up because they had spent so much time and they weren't getting anywhere. So students don't just, try for 5 minutes and give up. They're trying for hours. We're not able to make progress that was useful in this open-ended system without having hints in the first few problems that sort of helped them learn the whole process. We also looked at, can we add expert data to the system to begin with to actually even have less need for some student data before we could start giving hints. And what we could show is that we actually could get rid of this initial ramping part for the data and go ahead and start at over 50% hints for the first few students if we had expert data. Just a few problems worked by a few examples, experts put into the system. And we repeated all the data, and we just showed that we were able to start a lot sooner with something seeded with expert data. But one of the problems with that is if you just add some expert solutions into your system, then you're not getting that wonderful benefit of the zone proximal development of like matching a student with another student that did the problem like that. You're matching the student with the expert, which is what most intelligent tutoring systems and expert systems do, is they're comparing the student approach to the actual expert-generated optimal solution. So what we actually do in our system is we alternate which problems have hints, so we still collect that data without any hints at all on some of the problems, because most teachers don't want hints on every single thing that their students do. So we just alternate it, so we get that diversity of the student data, and not just sort of the trailblazing effect, which we have observed since then. We have observed that in systems where we have the hints, the students do tend to do more what the hints would tell them to do. And they also modify their behavior if they do something and then they figure out that they're not going to get a hint from that, they delete it. And they'll go back to something that they could have got a hint from, even if they're not asking for hints. So we actually have our little button on the side of our proof tutor that says it's yellow when they can get a hint, it's gray when they can't. And they will delete stuff if they see that the hint button goes away. It's really interesting. So we haven't done anything with that, but I think it would be cool to see, like, basically what that is telling them is, has anybody ever gone this way before? So like, we all talk about the road less traveled, is a great place to go, but not when you're doing your homework for discrete math. You should do what other people have done. So actually, speaking of what other people have done, so when I told you that we first were able to assign values to the states the students were in these process-driven problem solving, we labeled the goals. We said, okay, this is a done proof, this is a completed proof, this is a complete proof. Our system can detect that, but what if you're an open-ended system that can't detect if the problem is actually solved yet? So what we did is we said, okay, when you do a proof, this also answers another question. If you're solving a problem, you have lots of steps. Just because you finished doesn't mean that everything you did was good, right? You realize that. Like when we submit a paper to a conference, there's a whole lot of stuff that got deleted because it was bad or wrong, but it's not in that final version that we submit, right? But students, you know, when they're in a learning environment, like there's errors are still in there, and or even if they weren't errors, like it was a valid thing, like regular English sentences we delete from our paper, there's some reason why we delete them because we don't need them for the final purpose. So the idea is like just because somebody finished something doesn't mean everything they did was good. So we wanted to see how many of the steps that students do are useless, like are not used in the final proof, and you can recursively figure that out by looking at their solution and seeing. Did each step get used? And that's a computationally intensive process to do. But we did it, and we actually were really happy to find out that frequency was actually a predictor for whether something was useful or not. So let me explain that. So if you take a single problem and all the things that anybody ever did in solving it, and you make a list of them, and then you just count how many people did that thing. If more than 7 people did something, it actually turned out that it also correlated with being useful. So the things that less than 7 people did were not useful. So the cool thing was we didn't have to do a computationally complex process to look at useful stuff. We could just say, if a lot of people did it, it's useful, and if not a lot of people did, it's not. Now that can only happen in a system where you've got like 70% correct, right? Or people finished the problem, but you have classes with normal curves, and people do actually get 70% of stuff, right? So we do have data where people are actually able to do things. So we did not label correct solutions. So we actually came up with a way to actually think of the states as a list of all those things that you derived, which is what it is, right? And then for every useful thing or frequent thing that you did, we gave 5 points to that state. And for every not useful thing, we gave -1. So if almost nobody did it, we gave a -1. If other people did it, we gave 5. And so the value of every single state was just the sum of how many useful or frequent things did you do times 5 minus how many not frequent things did you do. And then we used that to assign hints to people. And then we said, okay, if we do that, how different are the hints going to be? So that's a graph, by the way, of statement frequency. So there's a lot of things that aren't very frequent. So we actually came up with 384 states that could possibly have hints generated. And 204 of them only had one choice of what they can do next. So both hinting systems were going to say the same thing. So then there were 180 that had different choices. And then we compared the two methods, and they agreed on the next best state in 91% of those. So we didn't actually have to know where the goal was. If we just knew that you did stuff that most other people did, then you were on the right track. And that has some wonderful implications for problem solving in MOOCs where we can't grade everything, right? Or we don't know what the content should be in a correct solution. If we can take this idea that if I can break your solution down into elements, and the elements can be compared to the behavior of everybody, and if most people are doing it, then it's probably right, and if nobody's doing it, it's probably not right. That's a nice idea. Okay, so then we started building a tool to look at these graphs, because when we talk to people about it, they're like, well, what does that look like? And so we wanted to build a tool where we could look at these and see what was going on, and these red arrows are if you make, so these are just a representation of states, so we make green boxes for goals, like you finish the problem. And the fat arrows, instead of actually having multiple arrows for students, we actually just changed to having fat arrows that show there's a high frequency And then the red is where there's a lot of errors. So this is actually kind of typical for our logic problems in that there's a few places where students make a lot of errors, and there's a few really common approaches. And we've used this idea not just in the logic tutor, but also for a game, the B-Loom game that I did mention before. And the students need to make a target picture. We give them a picture, and they need to plot points to draw that picture. It's like a picture made out of fat pixels. And so students can start with, say, a blank slate, and then they add a red square, so we can actually have graphical representations of the states as well, depending on your tutoring environment. So the picture that the students were trying to make here is this picture with 4 squares, and it's sample of students, their transition diagram, their state transition diagram for us is given here. And we've actually made a prototype system where we can load in all the data from students solving a single problem, and you can select, I know it's very hard to see this, but you can select areas of the graph and then make subgraphs and look at them. You can filter on frequency. You can look for particular steps, like let me see everybody who made a red square, or things like that. And this is a bigger network than the one I showed you before. And we've made some algorithms to try to simplify them so that they don't look so much like spaghetti. So we've actually taken out everything that's frequency 1. So this is a picture that doesn't have any frequency 1 things in there, because if I'm a teacher and I'm looking at this and I just want to see how students solve the problems, I don't care what one person did. I really want to see what most of the class did, or the top 3 ways that students did things. So another thing we're moving towards is not just visualizing this, but actually giving people just the top 3 graphs. What do those look like? And what do the errors look like? So we have some different tools. So we can filter on the top left, number 1. We can filter on node frequency, edge frequency, and on the value that we've assigned the states. We can search on the state descriptions, the names of the actions that they took. The bottom, number 3, you can make subgraphs. You can take out errors, because there's a lot of them. You can see in this graph, all the red circles are errors. And so if I want to just see what successful solutions look like, I can take the errors out. There's a mini map of 5 because we're zooming in and out of a graph, and it's kind of easy to get lost. And the rest of these are basically data from the text files that we're building a graph on. We did a really cool study. It took way too long to tell you guys about all this, but we did a really cool study where we actually had experts use our visualization tool and try to predict the kinds of errors that students made, and then use their hypothesis to direct their search of the data. And so this was actually mine. My guess was that students were guessing and not applying a strategy to solving a logic proof. So I've been teaching logic for a long time, and I know that one of the things that students do is they take every rule and they change it into an or statement because they don't like implications. Right? Like if, then is harder for students to understand than ors. So they change everything into ors. And that's useless because you really can't do anything with that, because most of the other rules that help you do things don't use or rules. So I looked for that, and I found that a whole bunch of students were doing it. So I found that 29 students were doing that, and that those students had a 59% success rate. So I was able to use the tool to actually find students that were doing a whole bunch of guessing and not applying a strategy, and figure out that they had a different success rate. Another thing we have been able to do is look at 2 different graphs of student solutions at different times. So these are students using the B-Loom game, and on day 1, this is the graph of what students were doing and solving a particular problem, and on day 3, this is the graph. So you can see actually they converge. So there's a lot fewer states on day 3. They learned how to use the tool, and they learned what they were doing. We've also done some clustering of the graphs based on social network analysis, and have been able to, this is what we're using to generate our sub-goal hints. So before I told you we were looking at being able to give more abstract hints instead of just the next step. So now that we've clustered these based on edge betweenness, and feel free to ask me more about this later, we can actually tell students, okay, instead of the next step, we're going to tell you you need to get on this other island in order to get to a goal, and we're going to tell you how to get towards that other island. It's sort of like if you're in Manhattan and you need to go to North Carolina, we're going to say get out of Manhattan, right? Take a bridge. And then we're going to help you get there. We're not going to tell you turn right on this street. We're going to say the bigger picture of where you need to go. And so this is a picture that we've actually done where we collapsed all those clusters, and then we were able to look at it from an expert point of view. It's sort of, what do these islands mean, and how are people traversing the problem-solving space? And the fat ones, again, are really frequent. And an interesting thing is that in this tutor, students can work from the top down, like what we call forward, or they can work from the bottom up. And we actually found that students were more successful when they were working forward. And so that's an interesting thing, because that tells us something that maybe we need to teach the students not just how to work backwards, but also how to work forward, so they can have that better strategy early on. And this is different kinds of representations. We're actually rebuilding our tutor. Like I said, we have to build it in JavaScript because Java's not supported anymore. And like I mentioned before, we showed that our hints improved retention in our tutor, and we've started doing something called survival analysis to actually tell what does that time in the tutor mean. I promised you I'll tell you about that. So if you haven't heard of survival analysis, it comes from medical literature, like research on drugs, and like how long people survive when they're on them. So it's kind of a weird thing to apply to a tutoring system. But we were looking for a way to tell what does time in the tutor mean, and how can we say that one condition, you know, causes less time for learning than another. But when you have so much dropout, and you can't do it because you've got so many people that drop in the tutor, you have to drop their data. Well, we don't want to do that. So what we're doing is we're modeling, you know, we're using survival analysis to actually make curves that will predict how much time in the tutor somebody would spend. And we can actually tell that students who are in our hint condition take 45% less time than students not. Our newest thing that I want to leave you with is that we've started this new thing called data-driven mastery learning. And so mastery learning is when you don't move on to the next concept until you know the previous one. Well, when you have an open-ended learning system, like for logic, I don't necessarily know which skills are going to be the ones that are going to get the student to the end. But I do know which students have finished in the past. So the whole idea of our new data-driven mastery learning system is to take the data from students who finished the whole system, break it up into some kind of intervals, like by time or maybe by problems, and then let's just take a profile of all the students that succeeded at those intervals. Then make that the target profile for new students who come along. Then when a new student comes along, compare them to that profile. If they're not hitting the same thresholds of knowledge of students who succeeded in the past, then make them do some more remediation before they go to the next interval. That's really the basics of that. And we've done that, and this is some pictures about that. But basically, we've actually shown that when we redid our logic tutor to do that, we can get a much higher percentage of the students to finish the tutor. So this is our original system is orange, with hints is green, and with our data-driven mastery learning system is blue. So this is percent completion of the tutor, so people who finished 100%. So you can see that in the control, the original system, less than 30% of the students were finishing the whole tutor. With hints, a lot more. We were super happy about that. But then when we decide, hey, are you matching, are you at the right level to go to the next level, we can retain more than 50% of the students. So with that, I will close and take a question.
That's very cool work. I was wondering, in the context of logic, you have a very small state space of possible steps that students can get to the set of expressions students can generate. Have you thought at all about how to apply this to more kind of open-ended domains? If students write a computer program, designing a circuit, or other types of kind of similar systems, like with much larger state spaces?
Thank you for asking that question. If I could have paid someone to ask a question, I would have paid to ask for that question. So I appreciate that. We're actually working on trying to build hint systems for programming for novices. And so we've been looking at what should the state representation be for sequential states in programs. And we've done some work on that. And we've done some hand analysis of some Java programs of students and actually seen that we can do a good representation. So what we're using for the state, we've tried a couple of approaches. One of them is called a linkage graph that John Stamper came up with. He's over there. A linkage graph is sort of tracing all the variables in a program and kind of making a regular expression of what's happening to all the variables, and then using that to compare two student programs for candidates for matching for hints. Although we haven't built that system, but I'm recommended for funding for a grant from NSF that will extend our work in that direction for programming.
More questions? I have one general question. So at the very beginning, you explained your guiding principles, and you presented lots of cool work. I have a question about the justice principle. So could you relate how all the experimental work, development work relates to it?
Okay, so the question is, how does my work relate to the justice principles? So justice is sort of like about equity of access. So most of my work has been in college discrete math classes. So of course that's already in the lead group of people. So I haven't been pushing the justice angle with this work that I was presenting you with. So I do other work in broadening participation, and I get, so we have a grant from the National Science Foundation from 2006 to 2016 to have college students do outreach, research, and service to try to get more students into computing. But also, the justice angle is I invite undergraduate students to work with me on their projects and to make new games and learning environments and to work on the educational data mining work and try to expand the access to more advanced STEM work to more students. So I'm not exactly using my EDM work to get to the justice principle. Although there's a little bit of it, right? There's an equity of, I'm not just treating someone as like, if you don't have an A, you're not doing anything good. So in this approach of giving hints, I'm actually not just saying, okay, I'm generating hints that are great for that student who's really already has an A. But I'm actually, so since our hints are sort of modified by frequency, we're kind of saying, okay, a C student might be matching with another C student, and the hint that I'm giving might be more effective for that student than the same hint I would have generated for someone with an A. So, and so the idea is there that every student can potentially achieve the A level, but they might not have to go the same path to get there.
I have a question. Which kind of measures do you take to avoid crushing creativity? In a way, if I have a completely different view that most of my fellow students, and I can solve the problem anyway, how you avoid the system to keep saying this guy got wrong, got wrong, got wrong?
Well, that's a great question. So we don't actually tell students they're wrong. So a hint system our hint system is on demand, so they don't get a hint unless they ask for it. And so if someone's doing something creative that that no one has ever done before, we don't say anything to them. So they're usually fine. And one thing we've looked at is that the students who don't ask for hints, but they're doing something that is kind of strange and we just don't have in our data set before, they're not asking for hints because they have this creative urge and they know what they want to do. Now, students who do wonky stuff that no one else is doing and they're asking for hints, they're not usually being creative. They're usually doing something, like they just tried something random. So I actually think that our system doesn't hurt those people, but it's not necessarily helping them. But the rotation of having hints on different problems in different semesters means that I can capture your creativeness, and then if someone else kind of comes along and is creative in the same way as you later, I will be able to give them a hint along the same path as you.
Thank you, Tiffany. It's time for the break, and there will be more questions and more discussion during the break. But by now, let's thank Tiffany for a very interesting talk.
seen screenshots of it because I'm on the live.
Right. It's going like that.
It didn't come as fast as the whole site. It should. Yeah, where you should be.
Do you have the URL?
I don't have any. I imagine that
Yeah, it has it. Yeah. But the email was sent by Matt. Because Matt's in redirect and it said that Matt just
so,
you were intrigued by the.
well, I'm intrigued by many of the things she said. As usual, probably over. But
First is strategies are metacognitive, expert novices, novice learners. In a lot of cases, come down to strategy. To solve a problem, expert just uses a better strategy.
Right, but it's unjust.
So if you want to assess,
I agree with
right. Strategy is something to do it's really inspiration. But you start looking at psychometric models and assessments.
And I think she actually understood what she
overall
believe that hit system
and most of them only look at correct and incorrect.
more opportunities.
I totally agree.
So that's the space where I'm looking.
So me,
Now, the reason that strategies are extra hard is switch. Every time something, a lot of people kind of, a lot of people make the wrong assumption that if somebody's using a strategy,
for more energy, you know, that's a fire.
They assume that people solve a big problem once and that's the only way they ever solve it.
So now really
When you look for strategy switching, you find it in 80 to 99% of the students.
so you know, I find it kind of
But even the concept requires a lot of people look for strategy switching. But when you do look for it, you find it. So modeling capturing strategies because we're switching problems is really difficult. I am trying, there is a statistical model called discription. Have you heard of that's why I ask. Some people are like, oh yeah, and some people are like, challenge is really exactly your response. So, what about latent class model?
And wonderful and research friendly, like, and philosophies and the staff themselves really want to see equality.
Models generally assume latent things contagious. Latent class models assume that there's clusters in the data and so screen.
I was just about to ask you about in the US,
it's not fuzzy clustering. Fuzzy clustering is like, I don't know if you're going to
instantly.
mixed membership is, no, I am very confident that you are half 1.5%. So when you have your kids both urinating and after. So no, I'm certain you're both.
those researchers have to like
Sometimes hard for people. But that's
the chances of one IRB
strategy
proving it
usage. That's exactly what we want. We want to know that you use this strategy about 50%.
It's a shared
strategy
project.
about 20% behind this other strategy.
No, I applied for University of Michigan.
Yeah, that is clear.
So Karen, I worked with her. She had to apply
It's that mixture of strategies.
I love it. It's really fun.
The mixture of strategies. So experts use this mixture of strategies. Novices use this. Both novices and experts switch. experts switch much more than novices.
So I like
Right. Well, that's yeah. So that's over the course of whatever you do, whether it's an assessment or a semester or whatever that would be. What's the mixture of strategies that this person uses at time Exactly. You only use one. Right. And so but that switching behavior is exactly what makes it harder to assess. About mental rotation. One place that people didn't look for it, they thought mental rotation was mental rotation. There's at least 2 mental rotation strategies. And figuring out which one people were using at an exact moment is really difficult. And figuring out which mixture they're probably using over several instances. Yeah. Right. And so yes, definitely looking at the features that trigger which I want to go there, I'm not there yet. But so in a lot of the idea one of the strategies of mixed membership to capture this, how much somebody uses which strategy. If you're measuring the right things, so there's a question of what's the performance. And if he doesn't have strategy with common multiples, easy identify strategies just with accuracy and response time. Certain bad strategies lead to certain very distinctive error patterns. Experts are also faster. But in other situations, you need different information, such as the sequence of actions. That's what I'm working on right now, is mixed membership markup chains, and strategy, markup process that generates sequence of actions. And a person has a membership record that says how likely they are to use the process. I don't know if it's going to work. I don't know what the conditions are going to be necessary for it. Ideally, you would be able to fit as an unsupervised model, and you would be able to go into your data and say, okay, here are all the strategies that students are using, and here's the different mixture of strategies that students are using. And so that for cognitive science discovery, in terms of discovering what students are doing, it can be a really powerful tool. But the real question is how much data do you need in order to fit it as an unsupervised model, and how strong a prior to be if you don't have that much data. It's a big, complicated, nasty model. You kind of got to put it as knowledge you're honest Right. Okay, so let's say you don't have a very big sample size. It's how much information it puts into the model. So when I say strong prior, it puts a lot of information in and really constrains things. So, for example, in the least common multiples example, you only have response time and time. If you have Yeah.
So the context
Exactly, but there I think you have to talk more about that structure. What you definitely is where you have a gathering information, you have integrated information, oh, I need to back something up so I can pull it out. And so we should still be able to talk it about. And again, what else? That was kind of what there are definitely some processes that still should be observable actions.
So